We are good to go, I guess. Hi, I'm Shravan. I work on applied crypto at Lagrange Labs. Today we have yet another panel with eminent folks and a bunch of prominent projects. And it's going to be on practical proving. How do you scale your proof computation, distributed proving, decentralized proving, and other problems associated in this space. So let me begin with a brief introduction. We have Sriram from PySquared, we have Jeremy from RISC-0, and we have Bo from Polymer. I'm going to let them introduce themselves, but can you tell us more about your projects? And this session is broadly about computing proofs, but I know that not all of you compute the same kind of proofs. Some of you compute ZK proofs, cryptographic proofs, CS proofs, whatnot. Tell us about what flavor of proofs you're computing.
Do you want me to start? Or?
Yeah,
sure. Hey, I'm Bo. I'm the technical co-founder of Polymer. In terms of proofs, we're working on generating cross-chain proofs for proving events or state between blockchains.
Hi, I am Jeremy, the CEO and co-founder of RISC-0, and we do general purpose ZK proving. We were the creators of the sort of first, ZK proof system that lets you run arbitrary code, and currently we're working on sort of the next phase of our system, which is Boundless, a mechanism for bringing ZK to every chain.
All right. Can you hear me? All right. Well, my name is Sriram Vishwanath. I'm also a professor at UT Austin. And I have to be honest here. My expertise is not in proving it. Well, I can prove stuff, but my PhD is in statistics and AI. So I'm an AI person. But I was lucky enough to meet a gentleman named Gregory Rochu, who's a professor at Illinois, who came up with the concept of pi squared. And pi squared is proof of proof, so the pi of pi, pi squared. The core notion there is to generate a proof using fundamental principles in logic and programming languages, a proof that's universal, that can apply to different settings, different languages, different VMs, and I'm happy to talk more about it. But if you ask me a very tricky technical question on that, I'm going to have to get back to you.
Okay, so we have a pretty good context of what's going on. So let me begin with something rudimentary, I guess. Tell us a little bit more about what's your approach to scaling in your projects. And I want to give a context, like I want to know what kind of challenges you had to overcome and why the design choice you made towards this. And yeah, that's about it. Yeah.
Do you want to go this way or that way?
We do the reverse this time. Switch it up.
Sounds good. I'll go first. So pi squared is based on a framework developed by Gregory called the K framework. It's essentially a universal interpreter as far as you're concerned. So you can take a language and interpret it to math. And when I first saw it, I was amazed. Trust me, he has been working on it for 20 years. I was the one sitting there getting amazed. So what does that mean? You can take a program you write, and eventually AI will write the program for you. And that program can now be written as a math proof. And that math proof then becomes a ZK proof, using RISC-0, using all the partners that do ZK proofs. So why is that very cool? The reason it's very cool is that you can now run a program in a GPU superpod or in a bunch of edge devices or wherever. That program now generates a math proof that it ran correctly. And so you can do off-chain compute on steroids in a manner that is extremely scalable. And that's why I got interested. As I mentioned, I'm an AI guy, and I wanted to see AI programs be run that way. And it turns out you can. So that's the approach to scalability.
Sorry, Jeremy, I'm very curious about, quick question about when you say math proofs, what would be the typical size of those proofs before you get into composability?
So the math proof really depends on the size of the overall program, but it's going to be in the megabytes size.
Okay.
So it's a big math proof, and it's not zero knowledge. But with a zero knowledge proof similar to RISC-0 and others, it can be digested into a few kilobytes.
Yeah.
Yeah, I mean, I think with regard to scaling, at Risk Zero, we've sort of hit two major sort of scaling issues. The first one we realized was that when you want to prove the execution of an arbitrarily large program, how do you do that? You know, at the time we came around, the idea that you could run arbitrarily large things in ZK was not really the case. You made a specific circuit, it was a certain size, that's how big your program was. And so we basically came up with this notion of continuations where you basically break the program into segments. And then further, there's the question about how do you, in fact, parallelize that workload, distribute it amongst a number of GPUs, really make something that you can run efficiently no matter how big a program you do. And that sort of got us to the point of being able to run, you know, prove entire Ethereum blocks very quickly. I think we're now at about 30 seconds to prove an Ethereum block. We expect real-time proving to be just around the corner, certainly before the end of the year. And then the second real question is the question around scaling of the proving capacity, right? Like, we run a bunch of proving nodes, some of our partners run proving nodes, but how do you sort of build a sort of a market so that anyone who wants proving can get proving done, and that in fact the proving infrastructure is able to scale up and down as necessary based on demand, right? Which is really sort of the next phase. That's what we're working on with Boundless. So I think we've, you know, had one major scaling problem. We've basically solved that one, and so we're now on sort of to the next scaling question, which is we have designs for, but we haven't. We're still in testnet. So.
Okay.
I can talk more about this from the perspective of on-chain costs. I'm going to start with something that's not ZK first. So if you want to prove state between two rollups, let's say, and you want to do it via a storage proof. So let's say you implement RIP 7755, you do a storage proof of the rollup state on the L1 and the L1 on the in the rollup state of the other L2. These proofs are, I want to say, roughly over 16 kilobytes, 16 to 18 kilobytes, about 2 million gas to verify on chain. ZK is a little bit more efficient. You can do the proof verification off-chain, bring the proof size down. So I think like when you think about these cost trade-offs, you do ZK when the on-chain costs are greater than the cost that would have cost you to generate that proof off-chain via ZK. And then for Polymer specifically, we instead of doing storage proofs, we decided to go with event proofs. These are a little bit shorter, a little bit smaller. So the raw proofs in this context are roughly less than 1,000 kilobytes, or 1 kilobyte, sorry, 1,000 bytes, and roughly 60,000 gas to verify raw. So for us, like if a user is just wanting to verify a single event, we'll just give them a raw proof. If they're doing a ton of events, it can make sense to compress that computation via ZK off-chain.
Okay. Yeah, they kind of both talked about the trade-offs and so on. The question which I really wondering what is one key piece of innovation in your domain that's going to unlock the true scaling potential which you would ideally want? So it's hardware, distributed, or new algorithms. There's a whole plethora of options which we can think of, but what is that drives your projects the most?
So we'll reverse it again. So, all right. For us, latency is key. So the product offering and the customer segment that we're trying to service, they care a lot about latency. They want as close to block time latency as possible. Although I do know that EF is doing their experiments with like ZK VMs, and they also want to get the block time as well. But in our context, the block times of rollups are much smaller than or much shorter than the block time of the L1, and we see that trend getting shorter and shorter. So for us, I think it's not necessarily like splitting up the proof, so like breaking up the computation into many smaller parts and distributing it. I think if we're able to put the proof on a single machine, maybe like that's hardware accelerated, whether it's with ASICs or FPGAs, that would be more interesting for us because then you can get that pretty close. If you co-locate, especially if you co-locate that machine next to the sequencer, for example, of a rollup, then you can get these like low latency execution proofs from the rollup. And or like event proofs that we care about.
Yeah, I think in terms of sort of, I think your question was around sort of what new advancements are going to have a huge impact. I mean, I think one thing is I think historically I would have said a lot of these things related to performance, but the reality is that the performance improvements are going to just keep getting better and better. We have like a bunch of things in the line there. I think there's been almost a 4x reduction in ZK proving costs every quarter, which is like ridiculously fast. I think that actually, in my mind, the sort of one that's going to be the most like the new sort of breakthrough that's going to have a really big impact is with this idea that we're working on, which around proof of verifiable work, which is basically an economic mechanism to reward provers proportional to the amount of proving work that they do, which is going to allow, I think, the subsidization of proving costs, and will actually also sort of, I think, have create a new way to do a market of like verifiable execution that I think will have a really large impact. And we actually have just sort of announced the intent to do this. We will have hopefully having a white paper coming out very soon, which hopefully people will be able to read and find interesting. But I think that's the one that I'm really like super excited about in terms of like very big impact.
And I'm going to pick on my expertise for the impact. So I think, and I apologize, I know I'm not in the proving forum. I think a lot of the proving system is going to become clearer and more modular in terms of use. I think it's the scope of the applications that are going to need that proving system and what those applications are going to need it for and how integrated they have to be with it that's going to change. I see about 1 billion agents in 5 years, and about half of them requiring a robust proving system.
Got it. Okay. The thing that brings me to the next part is we have like new technologies coming up. Like this is slightly geared towards ZK. How are you folks thinking about the rapid change in cryptography? What I mean by that is like we have a new proof system coming along every day. That's a bit of a stretch, but perhaps every month. And how are you guys coping up with scaling each specific proof system or like moving to all of these new techniques? Yeah, so Sriram, you want to start?
I have to think about that. Do you want to take it first? Maybe?
Sure, yeah, absolutely. I mean, I think one thing is that I think the research in the ZK space has clearly been advancing very rapidly. And every time a new paper comes out, we stop for a moment, read it, and sort of try to analyze what impact is this going to have. And then based on sort of the relative performance benefits or improvements we could get, we decide whether to sort of like do much about it or not. Like in many cases, it turns out that like some advancement in the research might give you a 30% improvement in proving time, but basically removing some bottleneck, that's a pure engineering thing, will give you like a 2x. And the reality is the engineering hasn't even been like dialed all the way in, and so a lot of these advancements are probably lower priority. That said, I think there have been a couple of places where there's been major leaps, right? Like for example, the work on binary field-based proving systems with like Binius. We're actually working with Irreducible to do a reworking of our ZKVM in that system specifically because the delta there is quite large. Now I think the research rate at these kinds of things has slowed down somewhat, but it's the wonderful thing about research is you never know what's going to come out next month, and so other than following it, it's very hard to predict. So I think the jury is out.
I actually have a question for the fellow panelists. I haven't been following the research as much recently, but I wonder if there's been any research done on is there some like asymptotic like limit to how fast we can make proving or ZK proving of a program? Because my mental model is that you have the program which you can run using a regular compute. And that kind of sets like the ceiling, right? Like it can only get as fast as running it without ZK. But I'm sure that with ZK you're going to take a performance penalty. Is that like is there some fundamental limit to that performance penalty? Is it like you always like you can never break like 90%? You can never break 80%.
So to my understanding at least, I think the short answer is there probably is, but I haven't seen any research that actually sets a specific limit. So I think that the question of where that limit is unknown, at least from my knowledge.
There is a proof creation to verification to size trade-off. We don't actually know where the curve lies, but we have some bounds to it.
So what are those bounds?
I can get you the paper.
Oh, okay. Yeah. Cool.
Yeah.
Yeah, actually, I don't want to take the role of a panelist, but to answer your question, it's going to be as fast as, given a program, what is the best way to verify it? That is as fast as you can do ZK. Coming to the meat of what we do and that motivates the panel today is, can distributed proving and centralized proving coexist in the future and the way things are trending? We have a bunch of new technologies coming up, like hardware acceleration, algorithmic improvements, and all of it. Whether does it make sense to distribute? I know that Jeremy does continuations and so on, and it's in some sense that lets them do these things, but when centralized proving versus decentralized distributed proving, how do you guys see this space evolve? I'm not going to point fingers. You can start.
I guess I had another question. Sorry to ask so many questions. On the previous question, I was thinking about the K framework and ZK. My understanding is that they're like two fundamentally different things. My understanding is that with the K framework, you're creating a mathematical model of the AST of the program before compilation. And then my understanding of ZK is that you're essentially proving constraints of the compiled program opcodes. Mm-hmm. So as more of a computer programmer than a researcher, so from my perspective, like those seem like two different things. Is there like I would assume there's an order of magnitude improvement with K-squared because at the opcode level, it's very specific. And then at the mathematical object level, it's like very, yeah.
Actually, it's embarrassingly parallel with the mathematical proof level because essentially the mathematical proof can be decomposed into a lot of independent lemmas. And each independent lemma can be proven separately. And they're all composable. Mm-hmm. We can go into that separately.
Yeah, having looked at some of the stuff, there's some really interesting places where you can actually, in many programs, actually prove things about that change the asymptotic running time and actually improve it. It's like kind of some crazy stuff that these guys are working on. Some good things.
Happy to
share
more.
But to answer your original question about the centralized and decentralized, provers. Sorry, no worries. I think so. What's very interesting is, so we are working with Boundless on making it so that the proving can be requested in a way which is fully decentralized and censorship resistant and prevents, so that it is usable for blockchains that have the absolute highest requirements in terms of decentralization. I think there's an interesting point, though, that there's, I think, a little bit of confusion in the sort of decentralized proving landscape around the difference between decentralization and prover, how well distributed the proving is. Let's just call it prover distribution. In the sense that, like, I think some people are concerned about, what if there's only one or two major provers? Like, let's say a company built some really good hardware, and the hardware, they don't sell it, and they just use it for proving, and there's this centralization of proving power. What's interesting is it's actually a false concern in some sense, and here's why. When we think about these 51% attacks or things like that on blockchains, it's important that you never have concentration because the consensus fundamentally can be consensus requires 51% honest majority. And if you have more than 51%, you're hosed, or actually 2/3 in some cases, depending upon your mechanism. But anyway, I digress. The key thing, though, is that from a perspective of, let's say 90% of the proving is done by one very powerful proving consortium. Now, let's say that they try to, as long as the mechanism by which the requesting and the settlement of those proofs is fully decentralized, like in the case of Boundless, let's say it's a smart contract on the various blockchains, then what happens is if that consortium tries to, so for example, jack up prices or shut down, it becomes an instant arbitrage for somebody else to come in and provide proving. Or if that consortium decides to, like censor certain proofs, it becomes instantly possible for anyone else to pick that proof up and maybe for a slight, additional fee and prove it, right? And so I think that there isn't this sort of 51% attack. And so if you believe that markets function effectively, then I think that this concern about prover distribution is less concerning. And that's sort of our take on it. That's our opinion about it as a company.
So I heavily agree. First of all, this whole 51% attack is a misnomer. Even Bitcoin is attackable at 30%. And Byzantine attacks are far less likely than rational attacks. Most agents tend to be rational. And so selfish mining makes much more sense as an attack than, anyway, so this whole 51% attack, don't get me started, I can talk about it for an hour. But coming back, it is absolutely true what he said, which is that given the cryptographic benefits of this proving structure, which is not there in any existing protocol structure, the entire set of proof, 99%, could be generated by one entity. And if it messes up, there is an immense opportunity created for every other entity to compete. And so I'm just repeating what he said. But I think centralized proving will give you all the benefits of blockchain without any of the scaling issues that decentralization causes.
Okay, want to add anything else?
I didn't really have anything to add. Is the takeaway then that we don't need like large proving markets, that a few large provers?
I think we want markets where the capacity to prove and the ability to answer requests are open and truly decentralized and censorship resistant, but we don't really necessarily require mechanisms in, like, say, the auction process to guarantee that the little guys, get extra advantage so that we don't get concentration. I think concentration is fine, and in fact, actually economically both inevitable and will reduce costs significantly, right? So I think there needs to be a separation between the notion of concentration versus control, and as long as the control is properly distributed, concentration is in fact not a problem.
So would you use Ethereum's mempool as like the public?
Right.
submission?
In fact, actually, that is exactly what Boundless does. So Boundless does settlement. It uses smart contracts on existing chains to do the requesting and settlement, and then the pools of provers themselves can be as concentrated as you want, and you still have great decentralization properties.
Okay, that kind of brings us to an end. I wish I could spend a little bit more time picking their brains, but unfortunately we are out of time. Thank you so much for joining us today. Let's thank our speakers one more time.